Hi everybody, and welcome back to Super Awesome Calculus. I'm Augie Kennedy, and this is the test for Chapter 3, also entitled Differentiation Rules. Yeah. So, I had to do that one last time. Just give me that one last time. Okay, so the test today will be 5 questions, and it's going to cover everything that we learned in Chapter 3. But before that, I just want to mention 2 quick things. First, I'm electing not to go over the section on hyperbolic functions, the hyperbolic trig functions, just because we didn't go over those. You will use them in Calculus 2. I remember we used them several times in Calculus 2. If anybody out there really needs a lecture on it, let me know and I'll see what I can do about making one. Outside of that, let's get started with the big problem that I left you with yesterday when we covered linear approximations and differentials. So the question was this one. The edge of a cube was found to be 30 centimeters with a possible error in measurement of 0.1 centimeters. Use differentials to estimate the maximum possible error, relative error, and percentage error in computing the volume of the cube and the surface area of the cube. This is actually a very easy question if you picked up on some of the things we talked about last time. What do we know? We know that we're looking at a cube. It's a square with 6 sides, and I'm quite bad at drawing them, but that's a cube. And there's no way that anybody can see that, so let's do that again. Alright, so we have a cube. And let's get the inner square here. Alright, let's just pretend that all 6 of these sides are equal. The way that this works is that we know that the edge of the cube, one edge, is going to be 30 centimeters. Alright? And we know that the error, the maximum error, is 0.1 centimeter error. Or the error is 0.1 centimeter. Now, let's set this up. That's the diagram. We know, therefore, we can say that x equals 30 centimeters and dx equals 0.1 centimeter. That's the key observation. Knowing that, we can look at the volume of the cube. Let's start there. Volume of the cube, v equals x cubed. That's the volume of the cube. So what we do now is we differentiate the volume of a cube. And we get dv equals 3x squared dx. But this is really easy because we now have dv and we know what x and dx are. So dv equals 3 times x squared, 3 times 30 squared, times dx, 0.1. And if you do the math, that comes out to 270. Now, if you remember to calculate the relative error, we're going to take delta v, the change in v over v, and we're going to realize that that's approximately equal to dv over v, and dv is 3x squared dx, v is x cubed, and that's going to reduce down to 3 dx over x. But once again, we know what dx and x are. So that's 3 times 0.1 over 30. Okay? Or 0.3 over 30, which is 0.01. And in terms of percentages, that's 1%. So your answers are 270 is the max error, the relative error is 0.01, and the percentage error is 1%. For surface area, it's the same type of situation. We still have x equals 30, dx is 0.1, but we have surface area s equals 6x squared, that's the formula. So it would follow that ds is going to equal 12x dx. And sure enough, that means that ds is equal to 12 times 30 times 0.1, which equals, I wrote it down here, makes it easier, 36. Okay. Now, delta s over s is approximately equal to ds over s. ds is 12x dx. S is 6x squared. That comes out to 2 dx over x. And we know that dx, we know what dx and x are, so 2 times 0.1 over 30 equals 0.006. So that's your relative error, which in terms of percentage is 0.6%. So max error 36, relative error 0.006, percentage error 6%. If you can follow along with that, you've got a good idea of differentials. Now, time for the test. You know the drill. I flash the screen up, and then we go over the answers together. So here's the test. Ready? Let's go. Okay, everybody, I hope you did well, or I hope you think you did well. Let's go over the questions. All right, starting off, I asked you to find the derivative of the following basic functions, just as kind of like a warm-up. First function was y equals x to the n. Well, you should remember that y equals x to the n, this is the power rule, y equals n times x to the n minus 1. All right, that's the definition of the power rule. B, I asked you to find y equals e to the x. Well, you might remember that the derivative of the exponential function is itself, so y prime equals e to the x. For C, I asked you to tell me what the derivative of the natural log of x was. You may remember y prime equals 1 over x in the case of the natural log. For D, I asked you what the derivative of the sine function is, and you hopefully remembered that y prime of sine x is cosine x. And finally, I asked you what the derivative of the tangent function was, and sure enough, it's y prime equals secant squared x. Okay? That was question 1, nice and easy way to start. Now, question 2 was a true-false question. True or false? If f and g are differentiable, then d dx of f of x gx equals f prime g of x times g prime x. Well, you'll know that that's not true. That's false. Because this right here, f prime g of x times g prime x, that's the chain rule. But this here is asking us about a product. They want the product rule. So the correct answer would have been f prime g, or f prime x, g of x, plus f of x times g prime x. That would have been the correct answer for the product rule. So there you go. Now, finally, we have the 3 real exercises. The first exercise that I gave you was y equals e to the cx c sine x minus cosine x. And I wanted to know what the derivative of that was. Now, you'll notice here that this is a couple of things. It's a product rule, and because there's a c before the x, when you differentiate the exponential function, it's really, you're taking the chain rule as well. Because it's not just e to the x, it's e to the cx. Remember, you're working with c, it can be any number, it's a constant. If it made you feel better, you could plug 5 in or 10 in and see what happens at the end to give you a relationship with c. For instance, if you were to plug in 10 is c and you get 100 in your final answer, you're pretty sure that it's going to be 10c, you know, because that's the relationship. I just like to work with c. So let's go ahead and let's realize that we're taking the product rule and a chain rule type of issue here. So y prime is derivative of the first, let's call this f and this g. All right, so we've got the derivative of the first is c times e to the cx times the derivative of the second, which is, or times the regular second, which is c sine x minus cosine x, plus the derivative of the second. And the derivative of the second is c cosine x. Negative cosine x is plus sine x times the first, e to the cx. Now that's going to simplify into what you can do here. This is what it should look like. If you got that, that's great. But what you might notice here is that you have negative cosine x and c cosine x, and you got c sine x and a sine x, and you got two e to the cx, e to the cx's. So what you really have here is you can factor out an e to the cx from this sum, e to the cx, factored out, and we get 1 plus c squared sine x. And you can see that because with these, with the certain identities that we went over, the trig identities, you'll be able to get this whole little thing in here to turn into 1 plus c squared, because you're going to have c, and then sine x left over. So with some simplifying, this is your answer. But if you were able to get to step 2, you should give yourself partial credit, because this is the mechanic that you really need to know. You need to be able to get to this point. From here, however you choose to simplify it, that's entirely up to you. But this is where you need to get. If you got to here and you didn't factor anything, fine. If you got to here and you factored out an c of x and then multiplied the c through, that's great too. Then you'll get the factored answer. All right, so that's the third question. Now, the fourth question on the test. I gave you this equation. God darn it. Like that's going to work. Is there any hope left for this marker? I gave you x to the 6th. I think I may need to pull out the emergency red, but I'm trying not to do so. X to the 6th plus y to the 6th equals 1. Okay, and I asked you to find y double prime. And I'm going to have to switch over to red. Sorry, but there's just going to be no way that you can read this. Okay. Yeah, that should be legible. I'm going to rewrite. You are given x to the 6 plus y to the 6 equals 1. And I asked you to find the second derivative, y double prime. Now what you should do here is you should do what we did with implicit differentiation. All right? So you should differentiate everything here with respect to x. So we get 6x to the 5th. That's pretty easy. All right? Plus 6y to the 5th. But remember, since we're differentiating with respect to another variable, you got to have that y prime in there. Equals 1 with respect to x is 0. Okay? If you made it here, that's good. Now you remember you're going to isolate y prime. So we get 6y to the 5th y prime equals negative 6x to the 5th. Or y prime equals negative 6x to the 5th over 6y to the 5th. Or the first derivative, y prime equals negative x to the 5th over y to the 5th. Okay? That's y prime. So that's what we're going to write down for right now. Remember, we've got the original equation, x to the 6 plus y to the 6 equals 1. And we have the derivative, y prime equals negative x to the 5th over y to the 5th. Okay? Now, we find the second derivative. The second derivative is we're going to need the quotient rule because we got to take the derivative of that. So the derivative of, if y prime is negative x to the 5th, y to the 5th, we know that the denominator, we know it's going to be the quotient rule, and the denominator is going to be y to the 5th squared or y to the 10th. Okay? Y to the 10th. We're going to forget about that for now. We're going to write it up here for simplicity, so we only have to work on the numerator. Denominator, which I'm just going to call bracket D, is y to the 10th. So, y to the 10th is bracket D, x to the 6th plus y to the 6 equals 1, and y prime equals negative x to the 5th, y to the 5th. Using that, let's use the quotient rule on just the numerator for now to figure this out. Okay, so that means that we're going to get y to the 5th times 5x to the 4th, g times f prime x, minus x to the 5th times 5y to the 4th, y prime. Okay? But we know what y prime is. Y prime is negative x to the 5th, y to the 5th. Perfect, let's put it in. So y double prime equals, and we remember this is all over bracket D. Okay? Now y double prime is therefore 5y to the 5th x to the 4th minus 5x to the 5th y to the 4th times negative x to the 5th y to the 5th. Okay? But that's going to simplify more. Y double prime equals 5y to the 5th x to the 4th minus, multiply that through, and we get we get plus 5x to the 10ths over y, all over bracket D. But here's what we can do. We can multiply that y through. We can get rid of it. So let's do that. Y double prime equals, multiply y through, 5y to the 6th x to the 4th plus 5x to the 10ths over bracket D times y. So bracket D will now become y to the 11th, and we'll just keep it bracket D. Now, let's continue to simplify this. What we're left with now is y prime. Let's go ahead and substitute y to the 11th back in. Y prime equals 5x, or 5y to the 6th, x to the 4th, plus 5x to the 10th, over y to the 11th. And we can factor out 5x to the 4th. And what do we get? Well, we get y to the 6th plus x to the 6th over y to the 11th. But we already know that x to the 6th plus y to the 6th equals 1. So y double prime equals 5x to the 4th over 11. Right? No, there's got to be a negative in there. Doesn't there? Huh. Probably. Anyway, I think I messed up something there, but that's basically your answer. Yeah, that's your answer. Should be y to the 11th. Yeah. There you go. Yeah. All right. So that's y double prime. Now the last question was a relative error question, and this is, God, these have been really long lectures. I apologize for that. I'm trying to go as efficiently as possible. Okay, a window has the shape of a square surmounted by a semicircle. First thing we do, draw a square, draw a semicircle. The base of the window is measured as having a width 60 centimeters, so base 60 centimeters. With possible error of measurement of 0.1 centimeters. Use differentials to get the maximum possible error. This is really easy. X is the square, is the base. Dx is going to be 0.1. This is one of those differentials problems. The window, it's a semicircle, so its radius is going to be half of x. So radius equals x over 2. So we know that the area of this whole thing is going to be the sum of these two little areas. So A equals the area of the square. A square equals x squared. All right. A semicircle is going to be 1/2, because half a circle, pi r squared, but r is x over 2, pi x over 2 squared. But we know that x is 60. So, hold on a second. What we're going to do now is the first thing we're going to do is we're going to explicitly write out if the area of a semicircle, by the way, just so I can vocalize the shortcut, is 1/2 pi x over 2 squared, you'll find that that's the exact same thing as saying it's 1/8 pi x squared. So, therefore, if that's the semicircle, then the area of the whole shebang is that plus the area of the square, which is just x squared. So, dA equals 2x plus, well, there's another way to write this. Let's factor out the x squared. X squared, 1 plus 1 over 8 pi. Okay? Makes it a little bit easier to work with. dA equals 2x times that quantity, 1 plus pi over 8 rather, pi over 8 dx. We know that x is 60, dx is 0.1, so let's figure it out. dA equals 120 times 1 plus pi over 8 times 0.1, and if you figure that out, you'll get something roughly equal to 16.7 centimeters squared. And that is the answer. But that's how you get to the answer. You can factor there, I did that for simplicity, you could have 2x, but you're going to get the same thing. All right, Well, I hope that was somewhat informative, and thank you very much for joining me for Chapter 3, and I look forward to seeing you next time for Chapter 4. Take care, y'all.